Hey, Travis, is there a lecture we would have missed, or was that why there was two
Uh,
last week? Or
no, there wasn't one you missed or anything.
okay,
Yeah, this is the last one. Here's also we get Monday off, which is nice. I think normally we just leave that to like extra um, time for the capstone screencast. So okay, all right. So we're going to talk about a topic today. It's kind of a little weird to like wrap your head around the first time, and I still have to like review it from time to time. It's a little awkward. But it's called dynamic programming. And the main idea behind this is that when we approach problems, we can either like directly try to solve it, or if it's too complex to solve just directly, we can break it down into smaller pieces, solve those, and then use the smaller pieces to solve the bigger problem. And that second way is what we've coined as dynamic programming. Um, this happens a lot when you just use recursion in general, and then because you break the problems down and then build them back up. And we'll see how to kind of take those recursive solutions, tweak them a bit, and improve them a little bit. So in the agenda today, we're just going to be going over some examples, some cases of dynamic programming and like how you would approach it. Specifically talking about Fibonacci. That's a very common problem. And then the 0-1 knapsack problem, which has a lot of stuff in there that will help you with similar problems of its type. And then we'll talk about some takeaways and where you might use dynamic programming in the wild, in the real world. So to get us started, for those who don't know Fibonacci, it's a mathematic sequence, and the way that we generate this sequence is that the next number in the sequence is going to be the previous two numbers added together. So we start with 0 and 1. So you can see like the 0th number is 0. The first number is 1. And to get the next number in the sequence, we just take the previous two and add it together. So 0 and 1 is 1. 1 and 1 is 2. 1 is 2 to 3. 2 and 3 is 5, etc. And we just keep going. The last two numbers added together is the next one. So when we want to calculate what the 20th Fibonacci number is, we can start to see that like in order to calculate the 20th Fibonacci number, a more complex number here, I need to first know what the 19th number and the 18th number are. And that kind of starts forming us into this pattern like this. So we have a base case. If it's 1 or 0, we just return that value. Otherwise, I want to recursively call to get the number -1 and the number -2, figure out what those values are, and add them together to get the new value. The issue with this is that it makes two recursive calls and splits that into two different call stacks. So let's actually check out what this might look like. If I wanted to know, for instance, the Fibonacci number 4, if I want to know what the value of that is, and I put it into my algorithm here. If I do Fibonacci of 4, that means I would need to find Fibonacci of 3 and Fibonacci of 2 first, right? So I make the two different calls. So Fibonacci of 4 minus 1 and Fibonacci of 4 minus 2. And over here on the left side, I have to calculate all of Fib 3. And then on the right side, I have all of Fib 2. What are you guys noticing about this kind of split tree with these two recursive calls? Anything jump out at you as like, oh, that's kind of inefficient, or we're doing something multiple times, or
Uh, we're making the same call, yeah, to the same operand of fib multiple times. Like fib one is being called 3 times here, fib two twice, etc.
yeah. So if you look at this, like we have fib 0 is called twice here, fib 1's called 3 times, fib 2 is called twice. So we're doing a lot of like repeated work, and we're doing it repeated work on completely separate branches of the tree as well, right? So like there is a lot of just unoptimized calling where we have to like recalculate values over and over and over. This actually makes this problem extremely inefficient if you solve it this way. The time complexity is 2 to the power of n, which is exponential time. It takes, if you tried to run this algorithm as is on your machine, if you're trying to calculate the Fibonacci number higher than, let's say, like 30 to 40, you're going to have a bad time. It's going to start really chugging your machine. I think like mine was able to do like 42 in like 12 seconds, which is not very fast at all. And beyond that, it started slowing down like crazy because it's exponentially getting worse the farther up we go. The other thing is that we, as a side note, we have a space complexity of O of n, and that's just the height of the call stack, right? So how far down we go in our call stack is based on n. So that's not going to change much if we're using recursion, but it's important to see it in there. So let's actually see. I got a replit in here. This is just the algorithm here. And what's nice about this algorithm, in my mind, is actually it's pretty straightforward. You know, it does the work in a very elegant way. It's just not efficient with how it does it. So, for instance, I can get you know, the fifth Fibonacci number happened to be 5. Sixth number should be 8. And that's fine. But if I tried to get like let's see what 30 does. Okay, so 30 is still decently fast. How about 40? And you can see as soon as I make that jump, it starts slowing down a lot. Right? So 40 took a while. 45. And now it's taking an extreme amount of time because it has to do all those calculations. It has to do all that left side, all that right side, has a lot of duplicates that it's doing. This could take a really long time. I'm not even going to wait for it to finish. I think that we don't even need to worry about that. It might not finish for this lecture depending on how bad it is. So that's the problem, is we have too many calculations. We're doing all these branching and repeated stuff. So do you guys have any ideas of what we could do to maybe speed this up or help us out? Yeah, I saw it in the chat. Memo and caching. Simone, is that what you're going to say?
Yeah, I was gonna say like storing some of your results in an array or something so you can look at them later.
Yeah, we essentially just want to, if we figure something out, if we save that, then we don't have to calculate it twice. We know what the answer is. So we want to be able to store our calculations that we've done already, and then we don't need to look them up again. We can just look them up in our cache, in our memoized store, which is a order 1 operation lookup, right? If it's in a depending on what you put it in, sometimes you put it in like a matrix, sometimes you put it in an object, but you want the lookup to be constant time. And all we're going to do here is adjust our is adjust our formula just a little bit. So we'll add in a memo to our function call, and we still have our base case. So we still have the if it's 1 or 0, we can return that. That's still very fast. It's constant time. If it's not 1 or 0, first thing we do is check to see if we've already solved it. Is it in the memo cache? Is it there? If it is, we can just return it right there. And we don't have to worry about doing another recursive call. If it's not memoized yet, if it's not something we figured out, then we can make the 2 recursive calls and take the result and store it into our memo. So this actually reduces our complexity down by a lot. We only have to compute every single Fibonacci number one time, and then we saved that result. And we don't have to do it any other time. So all that duplicated exponential work, we've eliminated, and now we just have basically one line of that tree. So if I were to look at this tree here, if I'm memoizing these, then I basically start with this one. I go to fib 3. I need to know what these are, so I go to fib 2, get fib 1 and fib 0. Once I figure out what fib 2 is, I store that. I store that idea so I know what it is. Then I go up to fib 3, 2 and 1, I already know what they are. So I store fib 3 here. As soon as I go to the other side of the tree and I say, oh, I have to calculate what fib 2 is, it's like, well, no, I don't. I actually know what it is. I can just look it up on the table. So I've eliminated the entire right side of this tree. And if it were, another level up, I would only have to ever calculate one branch down, all the way down, to figure out what that value is, which is kind of nice. It eliminates a lot of the extra work that we're doing. So let's see what this looks like here. This is an example. This is the example of the memoize. Let me make that a little bigger, actually. So what I have here is I just added the memo as an object. And when I'm not doing my base case, I just check, did I already figure out what that value is? And if I did, I'm going to return it. Otherwise, I'm going to calculate the recursive call, and whatever the value is that I get back from here, that's what I'm storing in my object. And then, this line could go inside the else, or it's here, but this is like the final result as well. So when I'm running top down for 5, you'll see the first thing, it'll go all the way down until it reaches 2, figure out what that is. As it comes back up and figures out each of the other ones, you can see it starts adding those values back in. So it figures out what 2 is, and then from there, it can figure out 3, because 3 will be fib of 2, fib of 1, and it puts that in there. And then when it gets to 4, 4 is fib of 3 and fib of 2, but we already know what they are, so we don't have to recompute them. And we can get that value in there. And then finally, 5 is just these two added together. So it's all the same recursive steps, but we're just saving our progress along the way so that we don't have to do repeated calls that we've already done before. Does that make sense to everybody? Are there any questions about like memoize and like what we're doing with that? Okay. So there's another approach we could do for this problem. So that was called a top-down approach. And the idea with this is that we're going from the top and taking our complex problem and breaking it up into smaller chunks, and then taking those small chunks and building it back up to the complex problem. So we start with the top, we break it down, and then build it back up. And that's generally like, that's recursion in a nutshell. That's kind of how recursion works. There's another approach called the bottom-up approach. So instead of calculating from like Fibonacci of 20, breaking it down to like 1 and then going back up, we could start with 0 and 1 and calculate going up. And these are just typically done iteratively as opposed to recursively. So a bottom-up approach for Fibonacci might look something like this. So if the number is less than 2, we can just return it. Otherwise, let's start with initializing an array and setting it equal to 0 and 1. That'll be our starting array. And that's accounting for the first 2 values that we know. We know what those 2 values are. Then, starting at 2, we're going to take those 2 values, the previous 2 values, and add it to our new array. And then we'll keep going, and we'll say like, all right, so 2 added 0 and 1 together, position 0 and 1. Position 3 is going to add position 2 and 1 together, whatever values are there, and that'll be its value. Position 4 will be positions 3 and 2 added together, and we're going to keep adding and building up this array until we get to n. So this method idea is going iteratively building it up. Our time complexity is going to be, in this case, O of n, because it's a loop that's just going from 2 to whatever value we're looking for. And our space complexity is also going to be n, because we're storing each Fibonacci value going forward into this array. So right now we've already kind of hit the same time and space complexity of the top-down approach. Is there a way we could make this even better? Going iteratively from the bottom up? Jonathan?
I was curious, I know this is probably not what you're after, but like, what about like running scripts in the background for things that you like know you're gonna have to calculate, like just so that they're like ready to go when you want them? That's not like necessarily this problem, but
so I guess the question is like, what are you thinking the scripts are doing?
they just start calculating Fibonacci numbers so that they're already stored in the cache, and then from bottom up, and then it's like, however far they've gotten, they're already there. But
yeah, so in this case, that's kind of essentially what this problem is doing, right? So it's not any, I don't think it would save you any time because you still have to calculate those numbers, and this is calculating the numbers.
Okay.
I see what you're saying though. Like if there were some complicated stuff and you could have a script on the side running it, but in this case, like, we don't have any numbers, so we would need a script to figure out all of them going up, right? And this is already kind of calculating as we go.
Okay, so if you did use a script, you still are like, well, what would make the script faster, right? Is that?
Yeah, it'd still be the same problem, right? Like, how can we make the script better?
Okay.
Because this is essentially like what the script would be, right? If you need a Fibonacci number, this is your script code to figure it out. Yeah. So I'll let you guys think about like maybe how we could improve this problem a little bit, but I want to talk about the steps we did. So with dynamic programming, remember what I said was the idea is we're breaking a problem down into smaller sub-problems that can be used to build up the complex problem. So the 4 steps you'll do is you're going to define what the subproblem is, like what's the basic problem. Relate those subproblems to solutions. So like in this case, I was saying like 0 and 1, and then when we add 0 and 1, we get 1 for the next Fibonacci number, right? So the subproblem is just every Fibonacci number before the one we need. Jonathan?
Yeah, I had another idea. Since I minus 1 is essentially going to be the I minus 2 of the next one, you could like somehow pass that along. But yeah, that was just a.
Yeah, I think you're starting to get on the track of what I was going for. We'll talk about it in a second. Nice. So the idea here is that we start with subproblems, and then when we get to 3, we have 2 options here. We can either do a top-down approach or a bottom-up approach. If we're doing a top-down approach, and this is completely a fine approach, right? We saw that it got us the same like time complexity solution. Is if you do recursion and you find that the recursion is doing a lot of repeated steps, you memoize it. So recursion and memoization is like one way of solving dynamic programming. And I think this is probably the most straightforward approach, because I think like the recursive solutions tend to be easier to think about. So if you're ever on a problem and you're like, I'm not sure how to do like the bottom-up approach for it, but I know what the recursive call is, think about just memoizing the recursive call, and that will give you that same result. The other option is to do a bottom-up approach, and this says build a dynamic programming table. So in this case, we made an array for Fibonacci that we calculated going up. We'll see another use of this dynamic programming table in the next problem, and like how we could use it in a different way. But the idea is like we're kind of starting with our base small problem and building up in this table to a final solution, and then use it to solve the original problem. So I'd asked if we could do better. And actually there is one thing we can do for Fibonacci specifically that's a little better. When we're going bottom up, we don't actually care about all of the Fibonacci numbers that are not the final answer. When we were memoizing it, it was important because there was a lot of other branches and other calls that were repeating. But when we're going bottom up, we're actually not repeating ourselves very much, right? As soon as it's beyond n minus 2, I don't care what those values are anymore. So we actually only need the 2 previous numbers to calculate the next one. We don't need the whole array of numbers. So another way to improve this is just to, and it doesn't increase time complexity. This is purely space complexity. But instead of having an array, we just keep track of those 2 specific numbers. So we start with 0 and 1, and we just kind of move them along. So in this case, we have 3 variables, n1, n2, and temp. So temp will be the kind of next number we're going for. And as long as we're not at the end yet, we're going to get the next number by adding the previous 2, n1 and n2 together. And once we have that next number, we then shift up the other 2 variables. So in this case, move n1 to the next number, which is n2. And n2 becomes temp, which is the new next number we found. And then we just keep using those n1 and n2 to find the next temporary number until we reach the one we're looking for. So this eliminates on a lot of that space complexity of having an array of n numbers. Now we just have 3 variables that we just rotate around until we get to our final result. So I think that this solution is typically like if you were in an interview, this would be like the best solution because it has the space complexity at O of 1. It just has 3 variables as opposed to an array of n numbers. And it still has that same, like, it solves it really quickly. That being said, the memoized solution and the previous bottom-up solution are also valid solutions. If you're doing the bottom-up, though, this is kind of like the ultimate goal is to have like your space complexity also very small. Before we move on, are there any questions about like the Fibonacci problem or how we solved it with dynamic programming?
Can you redefine like dynamic programming? It's just breaking it down into smaller steps, like any problem that you do that with?
Yeah, you take a complex problem and you break it into its smaller sub-problems, like smaller sets of problems. And using those smaller sets of problems, you were able to calculate the more complex one. So it kind of builds it back up. That's how I would define dynamic programming. Okay. So let's do the second example here. So let's go backpacking. This is a very popular problem. It's called the 0-1 knapsack problem. The idea with this is that we want to write a function that takes a bunch of items. So we'll have a bunch of different items, and those items will have different values and different weights to them. And we can only fit so much in our knapsack, so we want to actually put in the most valuable items into the knapsack. So we want to maximize how much value our items have and fit as much as we can into the knapsack. So the reason it's called 0 or 1 knapsack is because it's a take it or leave it kind of thing. So when we look at an item, we have 2 options. We can either take that item and put it into our knapsack, which would be a 1 for like a success, or 0 and we say we want to leave that item and don't put it in the knapsack. So in this case, let's say we have one that can carry 4 pounds of goods. So we have 4 pounds to work with, and we have a set of items to choose from. Each have their own values. We're calling them happy units here, but they could be things like, dollar amounts or any sort of value associated with them, and how much it weighs. So we need to maximize how much value we get out of this, how many happy units in this case, while adhering to our weight constraints. So we can't just put all the items in because that's, that'll be 8 pounds and our knapsack only holds 4. We don't want to break our backs with this. So in this case, let's say we have 3 items here. We have a boombox, a laptop, and a guitar. And I could take the boombox. If I take the boombox, that means I've capped out on my knapsack carry weight. It's 4 pounds. I can just take the boombox and leave the other 2 items. That's one answer. I could also take the laptop and have no other items. That's also an answer. I could take a guitar and a laptop. And it's like, which one is going to give us the most value overall? So the answer here with 3, it's a little easier to see. If I take the laptop and the guitar, I have 3,500 happy units as opposed to the 3,000 from the boombox. But if I start having 6, 7, 8 items, this might be a little harder to just visually see. So we want to have a program that can kind of calculate this. What are some options for what we could do? Like, what are you guys thinking for how could we solve this problem? if I had to write this in a function, like how would I start? Yeah, Kevin.
So I was thinking you would probably calculate their efficiency, their weight efficiency, and then sort of put them in, starting with the most efficient items.
Okay, so maybe you're starting with the most efficient ones. So I guess the question would be like, how would you calculate their efficiency?
Would be like their weight divided by the
Kind of
happy
a
units.
evaluate
Yeah.
ratio, maybe. Okay, that's one idea. Simone.
I think my like brute force solution might be to come up with every possible combination of items that doesn't exceed the weight limit. And then from there, like find the one that has the most value. I think that would be pretty easy for this problem because there are only 3 possible items, but if you had a lot of items, that would take a long time.
So just out of curiosity, do you know how many possible sets there would be for 3 items? Like ignoring the weight problem, like how many sets?
Oh, ignoring the weight problem, that would be 3 to the third, right?
Close,
No?
close. It actually ends up being 8.
Okay.
There's like one that gets duplicated or something. So the reason is because each one has an option of take it or leave it. So if you look at like the 2 options times the number of items you have, right? Or to the power of the number of items you have. So in this case, your 2 options to the power of 3 items, that's 8 possible sets of these take it or leave it options. However, just like you're saying, like if we just add 1 more item to this list, the number of sets we have to create goes up from 8 to 16. Right. And this is also like, obviously this is a little bit reduced because we could have things like, you know, if they are beyond the weight limit, like we won't look at those sets. But there also could be definitely problems where our knapsack can hold all of the items and we have to figure out better organizations, right? Jonathan.
In terms of representing it in something, can we do a graph to represent it?
Yeah, and we actually we'll be using a matrix to do it, but the matrix is also a way of representing a graph. So yeah, we will be showing that in a little bit. I'll come back to you for that question to see what you were thinking about it. So if in an interview, if you really can't figure out a good starting point, I think like explaining that you understand a brute force approach is probably a good way to get going, and maybe the interviewer might prompt you in more of the correct direction here. But like, I think having an answer is better than just sitting there with your twiddling your thumbs, right? Like, if you know it's an answer and you know it's inefficient, like let them know like what do you know about this. But yeah, essentially the brute force solution is to create a set which includes the item and a set which doesn't include the item, and then recursively adds the remaining items to that set. So we end up getting these different trees of sets where we have zeros and ones for whether we include them or not. So things like no items included would be 0, 0, 0. We would have like 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, you know, and like all of those different sets enumerated out. And then from that list, we could say like, oh, don't include the ones that are too heavy or not heavy, or, you know, things like that, and then figure out what's the maximum value between the remaining sets. Something like that. So if the total weight does not exceed capacity, we make these sets. And then figure out the maximum set that we can make out of those. All right. Going back to you, Jonathan, what was your idea with the matrix or the graph?
It's not fully fleshed out, but it would be like you'd essentially have like on the sides of the graph, you'd represent each row and column with each item. And then inside of the matrix or the graph, you'd have a 0 or 1 representing whether or not you're taking them. Or maybe you'd have their weights in there added together. Not totally sure.
No, I think you're actually on the right track, which is really cool to see. So one of the ways we could solve this is if we're really thinking of like dynamic programming, we want to break this problem down into the smallest subset of the problem, right? So one of them might be something like, if I have one item, what are the times that I would take that item or not take that item, right? So I might make a graph that looks like this. So each row in the graph is going to be each item that I have, and the order of the items here doesn't actually matter. You'll get to the solution in the end. But each column is going to represent a stack size. And the idea here is that as I go from the top left to the bottom right, I'm going to fill out this grid starting with the smallest problem, which is I have just the guitar as the only item I have, and my knapsack has a value, has a weight of 1. Can I put the guitar here? It's kind of the question. So the smallest subset, and I'm going to use everything that I filled in as I go further and further to the right, and by the end, this final box at the bottom right should have our answer of like what's the most value we can get out of this. So let's actually go through this grid. I drew one out. Actually, I haven't looked at this one yet. All right, yeah. So we have our essentially our 3 items here. We have a boombox, a laptop, and a guitar, and we have our different units for them. And this talked about this, and I'll slack out this diagram as well with all the slides and stuff at the end. Actually, let me need to put my battery in here. Okay. So I'll have this diagram out for you guys with all the slides as well, so you can go over it. But it talked about the first one is just try every possible combination until you figure out which one is the good one. In this case, it was kind of easy because different combinations just didn't fit in our knapsack. But if they did, we would have to check all of them, right? Let's look at this solution though with the graph here. So the first problem we want to figure out is for this cell, if we have a carry weight of 1 and we have a guitar, like is it better, like first of all, can we put it in there? Because if we can't, then it's going to be a 0. If we can put in the maximum value we can have for that amount of weight. So in this case, for just the guitar and one spot, I can have the guitar, which is the 1500 value. So then I look at the second cell and I say like, okay, if I have 2 weights, if I can carry 2 pounds of things and I just have a guitar, what can I do? Well, I can only put in just the guitar, right? There's not any other items. It's just the one guitar. So for the rest of these rows, as I increase my weight with only one item, that's the most value that I can have. I can just have that item in my knapsack. So you'll see here we actually filled out this top row. As the weight increases for just guitar, the best thing I can do is just have the guitar there. If, for example, this was the boombox, right? Then all of these would be zeros, and the last one would be the boombox. Zero meaning I can't carry a boombox if I don't have the capacity for that. So far I figured out, like, with just a guitar, like, what's the most optimal thing for my 4-pound knapsack? Well, it's to take the guitar. Let's introduce now a second item. Right? This is the second row going in there. I want to know if I have a boombox and a guitar and one carry weight, what's the best item I can put there? Well, in this case, I can't put the boombox in there, right? This is too heavy for a carry weight of 1. So I have to look up at the previous cell and say, like, what was the best one with just the items that aren't the boombox? In which case, it's the 1500. So I'm going to put that there. So in this case, like, I can't add a boombox to any of these cells, so I have to use just the other items, in this case the guitar, to fill that in. So I'm going to put in the 1500s here. Basically at this point, between a boombox and a guitar, for anything less than 4, if it's 3, 2, or 1, I have to use the guitar. Does that make sense so far? So this is just looking at those 2 items. Now that I get to 4, so my knapsack can carry 4 things, I have to now think about this. So my boombox is 3000 value, and my guitar is 1500 value. So the question is the boombox going to be more valuable than just the guitar here, right? So 3000 versus the 1500 for the guitar. In this case, it is. So I'm going to add that as my value here. This is the most I can get with these 2 items and a stack of 4. Make sense so far? All right. We'll start using the rest of these cells in this next one. This is where it kind of gets, like, really cool. So the laptop starts out in a very similar way to the boombox, right? It's a weight of 3 pounds. So for the first 2 pounds, like, we just have to kind of use the answer from the previous row. So in this case, since I can't pick a laptop when it's less than 3 pounds, I just look at the row previously and say, like, what was the maximum value that you had? It was 1500, so I'm just going to mark that down here. Same thing with 2 pounds. When we get to 3 pounds, 3 pounds says, okay, what was actually, what can we do? If we pick the laptop, that's going to be 2000. And if we do that, there's no more weights to check. So it'll be 2000 here. And we compare it to what the previous row's optimal value was 1500, and we say, like, 2000 is better than 1500. So I'm going to put the 2000 here. For this last row, to figure out with all 3 items and 4 carry weight, what's the best value, we need to look at the laptop. If we choose the laptop, that means that we have 2000 here for the laptop. And because it's 3 weights and not 4 weights, we actually have to look at what we can do with 1 more carry weight in the previous row. So I look back at 1 carry weight in the previous row and say, oh, if I have the laptop here, I can also add a guitar. because I still have one weight left. So remember, this previous row is all of the other items at different, like the best version of every items at each weight. So if I have the 2,000 here and a 1,500 here, the total is going to be the two added together. So the idea is like, as you're going up, you're kind of looking at, if I pick yes and put my item here, how much weight is left? If there is no weight left, then it's just the item versus the previous value. But if there is weight left, then I can check the table for what the previous row had for that weight. Because we already know that answer. Like if we have one weight left between the other two items, I know that the optimal value is going to be 1,500 for one weight. And I can slot that in there. So here's kind of the rundown of the formula. So the row that we're looking at, the row and column we're looking at, is going to take the maximum version of the previous max, so the one that's right above it. So in this case, for this cell here, it's going to look at the row right above it, take that value. Or it's going to take the current item, so like as if we are accepting that item, plus the value of the remaining space. So one row up and whatever the remaining space was. So in this case, in this cell here, the 2,000, there was no remaining space. So it was just the value of that item. But in this cell, there was still 1 pound left. So we had to look at the remaining space of that previous row. And it takes the maximum of these two, and that becomes the new cell. So in this case, we're basically solving every small problem before we get to our final answer here. We're solving for every possible weight and every taking or leaving the item, like which one's more beneficial at each step of the way. Can anyone think of like the runtime of this algorithm? I know it's kind of a weird thing to think about. So we have to do calculations, right? These calculations, and we have to do it for every item and every weight. So what would be like the runtime? Any thoughts? If it was just one for every item, that'd be n, right? We just go through each item in the list. And then we're doing it that times the weight. So I think the runtime here would be n times c if we use c for the weight, or whatever the number is for the weight. So number of items times the weight that we have. And that's how many calculations we have to do. A little bit better than like exponential stuff. It's just it's a little more straightforward. It's a factor of n. Any questions on like this setup of how it was solved? I will also show here. Let's see, where is it? I had it somewhere. Here it is. Okay, this is the actual code, and it has the steps in there. written out. And actually, I'll Slack this to you guys now, so you can walk through it if you want to. I will also make sure that like all these links are available to you guys if you want to review them. But essentially, this is kind of the setup. So we start by making the array, and we set up the array so that it's all of the capacities, all of the weights, and all of the items. Like get the n by get the number of items by number of weights into a grid, and fill them all with zeros. We just start with zeros in all of them. Now this one also added a row for like a 0 weight, which is often one thing that you'll do with this kind of problem is you'll have like these like 0 weights on the sides. It'll help with the calculation in the future. And then what they decided to do, so this was populating it all with zeros. The first thing they did is if we only had one weight, if it's not more than the capacity for that first item, if it's not more than the capacity, then we're just going to add that item to that row. So this was that just having the guitar, and like, does the guitar make sense to add here? So you can see it starts with 0. At 0 weight, we can't pick the guitar, so it's just 0. But at 1 weight and up, we can add that guitar, so it puts that into that row. So this kind of gives us our baseline first row with the guitar. Now, for all of the rest of them, we're going to have 2 values, and the value 1 will be the item, the value of, let me get this right, if I get it right. The value if we pick the item, and value 2 will be if we exclude and don't pick the item. So if we do include it, first of all, we need to make sure that it can fit. So does it actually work at our weights? In the case of the boombox, right, we could only actually choose the boombox when we got to the weight capacity of the boombox, right? So like it was 4. So until we're at weight 4, we can't actually pick it. Once we do, then we can take that value and see if that value plus any other remaining item for that weight, that'll be our total. So in this case, it picked, let's say the boombox, it got us that value. And then this is on slot 4. So it's basically said, let's look at the previous row, and is there anything else we can fit in there? Well, if we're at 4 weights, when we subtract 4 off of our weights, we'll end up at 0, and we'll add 0 to our total. So the value at this spot for a boombox is going to be 3,000. For value 1 is 3,000 plus 0. Then we get value 2, which is just the previous row. How well did the previous row do with this much weight? 1,500. And we compare the 2 of them and take the bigger one. So in this case, we took the 3,000. When we got to the laptop, the interesting thing was here at the 2,000, where we decided 2,000, picking one laptop was better than picking the boombox and the guitar at that same weight, which was just 1,500 because it could only fit the guitar at that. And then the last one saying we picked the laptop, so the value of the laptop plus any remaining weight of the previous row. So in this case, the laptop was 3. That left us with 1 weight left. So we have to check what the previous row did with 1 weight and add that to our laptop. And that's the most we can get out of that spot. And then compare it with the previous best for that weight. 3,500 versus 3,000. So by the end, you get all the way to the bottom, and then the bottom right of your graph, of your grid here, becomes your solution. So like I mentioned before, the time complexity here is n times m, where n is the number of items and m will be the maximum capacity or the maximum weight of there. And the space complexity is going to be the same as the time complexity here because we're storing that many values in there. Are there any like follow-up questions about the knapsack problem? I think, and that one as well, and that one's pretty complex. So I think one thing that would be good to do, especially before the rest of the reactors this week, is kind of review that knapsack problem. Maybe watch some other videos as well, getting more explanations of them. It's a very common problem you'll see. And, you know, because just hearing me say it, especially in only 30 minutes, is like, it's a lot to take in. So definitely review this. I think it'll help you when you go to the reactos in the rest of the week as well. But also just remember, like, if you're in an interview and you can't think of that off the top of your head, that's okay. Start with that brute force solution, get a solution down, explain why you think it's inefficient, right? So be able to explain the time complexity of your solutions and work from there. Going back to dynamic programming and the steps here, start with those subproblems and you relate those solutions back to the full problem. So in the knapsack example here, the subproblem was, what if I have one item and a capacity of 1, or one item and a capacity of 2? That's a subproblem. You know, does it fit into our knapsack here? Can I actually put the item in there? Then you relate that solution to the next subproblem. So if I have 2 items, the question is, well, can I do better by picking this item, or do I have to use what I figured out for just the first item? And you kind of just go over it again. Again, with dynamic programming, step 4 is kind of the big takeaway. You can either do a recursive and memoized solution and do a top-down approach to this, break it down, build it back up from the top down, or you can use something like these table solutions and build it going up from scratch. And that's kind of the ways that you approach these problems. So if you can't think of like the bottom-up approach, because the bottom approach does take a little bit to think about depending on the problem, try a recursive solution. Try to do something like that, and try to memoize the solution there, and that might actually be good enough to like get the time complexity down. A few takeaways. Sometimes dynamic programming is just careful brute force solutions. When I mentioned like adding memoization to recursion, it's still doing the bad recursion that's brute forcing it, but it's doing it in a clever way, which is like making us not do extra work. So it's kind of like a careful brute force. So you can think of it that way as well. The ways that you identify when something is dynamic programming or not, just ask yourself, like, do you have multiple options? Can you do multiple things? Or are there overlapping like subproblems? So if you're writing a recursive solution to a problem and you're not sure if it's dynamic programming or not, are you are you using recursion to break the problem into smaller problems? Like, is the recursion actually like reducing the problem to something simpler and then using that simple answer to kind of build back up? That would be a clear example of dynamic programming. As opposed to something that's like, are the subproblems dependent on each other? So something like merge sort uses recursion, but the and with these different answers, right? The solutions of the subproblem are independent, but we combine them back later. That's a divide and conquer approach. Whereas a dynamic programming approach, the actual problems we solve are like my top problem is dependent on solving the smaller problems. It's directly related. Yeah, and if you also see the subproblems repeating ever, like that's another indication that it's dynamic programming, and you can store those in a memo. And again, like combining those to the big solution is the big key with this one. The other two things you have to decide with dynamic programming is recursion versus iteration. And again, like the iteration might be like recursion tends to be a little bit more of a direct answer. Like once you get comfortable with recursion, I think it's a little easier to start with that route. The difference is here that iteration tends to be more space efficient usually. Usually don't have to use as much stuff to figure out the same problem. And it's more useful for when you actually know what you're trying to iterate through. If you're not entirely sure, then recursion might be a better example here. So in the case of Fibonacci, like we knew that we wanted to iterate up to n numbers of Fibonacci. So we had like a goal. Whereas sometimes it's a little more ambiguous about like where we're actually looping to. The recursive case, you know, it takes up more space in terms of like stack frames, but it has a clear way where we're breaking the problem down up to a base case. So we know, like, if we know what the base case is, we can just break the problem down to there, and it doesn't matter like what the steps are in between. We know we can get there. Also, sometimes you're using some pure functional programming languages. They might not have loops. So recursion might be the only way you can solve that. It's good to keep that in mind as well. All right. So some examples of dynamic programming just out there, if you're interested in like looking into it and seeing when you might use this. First of all, whenever we need to memoize to save time on something, that's dynamic programming. Like memoization is a big staple of that. So if you're ever doing something where you're memoizing, like that's a good example. Things like text justification, where it has to like, you know, move everything to a certain line in there and justify it, left justified, right justified. That's a CSS example that is a good problem. How much text can fill up the margins effectively, things like that. Comparing like DNA sequences or gene finding, like oftentimes when you're comparing, you're doing subsets of the problem to see which one's compared, and then build back up to see if the whole thing is comparable to each other. Converting one string into another is a big one. Anytime you're doing like spell checks, autocorrects, things like that, where you're saying like, oh, it's only, you know, this many off of this other answer. Things like that. Also problems like shortest paths with the different, you know, there's Bellman-Ford algorithm, Floyd-Warshall algorithms. These are graph problems. Finding the shortest path graphs are often dynamically done. You want to start by figuring out, oh, what's the path between shortest path between here and here, shortest path between here and here, shortest path between here and here. You kind of build up as you go. So you start with smaller paths to calculate the full shortest path of the whole thing. Speech recognition, face recognition are also things like that, where you want to break down the complexity of, let's say your face. You want to break down the complexity of that into the small parts that you identify as the face. Solve for those, and then build it back up to the full face to see if it's the same one as you're used to. Okay. Are there any final thoughts, final questions about dynamic programming, or like where to see it, or how to find it, how to figure it out? Okay. So with that,